Hello everyone. So we are going to solve a couple of problems now on column. So this is the easier problem first. So the problem statement is problem 1. So the problem statement is this is the interaction diagram given. Interaction diagram given. And also the column details are given. So this is the interaction diagram. So the interaction diagram is given and also the column of a column. Interaction diagram of a column is given. And what is the column? The column is the 4 rivers. So dimension is 400 millimeter by 400 millimeter. 400 millimeter and 400 millimeter. And clear cover is 40 millimeter. And longitudinal bar, this one is for 25 amber. And tie is 10 amber at 300 millimeter spacing. Also, it is also given, this is the column details and this is the interaction diagram. It's also given dead load equals to 50 kilonewton, 500 kilonewton, live load equals to 500 kilonewton, and eccentricity, like the force is applied not in the center, force is applied, so it's a B column is like that. And this is the river, and so stirrups, ties, and the force is applied here. Imagine there is a cantilever beam or something like that. So then the force is applied here. So the eccentricity from the center to this is the eccentricity. Eccentricity is given is 150 millimeter. So now the question is, this is the load given, this is the column given, this is the interaction diagram given. Question is this column safe for this load? This column, this is the column details and this is the load. Is this column safe? This is the question. Okay, now I'm going to solve it. It's actually extremely simple problem. So as you know, dead load and live load given. So the load is axial load 1.25D plus 1.5L. If we do put these numbers there, we get 1375 kilonewton. And as you know, this is the force B. So what is the moment? Moment is this force multiplied by the eccentricity. So the moment is axial force multiplied eccentricity. So 1375 multiply kilonewton multiply 150 millimeter. So you get 206 kilonewton meter. Okay, so now we calculated we got the axial load and we got the moment. So we got this guy and also we got this guy. And we know the column details. So now the question is this column safe for under this load? Under the given load. So is this column under the given load? So now axial force is 1375 and see this is the y-axis. So y-axis is axial and we put 500 200,000, and they look at the unit is kilonewton. So you got 1375 kilonewton. So put this value here. We got this 1375 here. And also moment is 206 kilonewton. So if we put this value here and check the unit is kilonewton meter. So unit is kilonewton meter, and actual load, that is kilonewton. So check the kilonewton. So this is the P and this is the M. So P in kilonewton 1375, M in moment 206. So now we draw the diagram. You get a point. So this is the point. Now in the last class, I told you that if it stays inside this, anywhere inside this, then it is safe. Anywhere outside this curve, then it is not safe. So this is safe zone. This whole part is safe. And anywhere outside of this curve, is not safe. So not safe. So therefore, since our moment force value and moment value intersected outside of this curve, so it's not safe. So then our answer is it is not safe. Or in another way, not sufficient. This column not sufficient. Not safe or not sufficient, same thing. So this column under this load is not safe, and this column under this load is not sufficient. So this is the problem solved. Now I am going to solve another problem. This is slightly longer problem, so I'm writing problem. So problem is problem 1, problem 2. So what is given? Lots of things are given in this problem. So first of all, the whole column is given, column dimensions and details. And then still river, and river. And dimension, H is 300 millimeters. B is, other dimension B is also 300 millimeters. So this main steel river is 420 amber, and this tie is 10 m tie. What is also given? It says that the cover, this distance, so cover, concrete cover is 40 millimeters. Not clear cover. That means not center to center. It's outside of the outer surface of the steel river to the end of the column. So those are all these things given, and also this values f prime c equals to 25 MPa, fy equals to 400 MPa. Yeah, that's all. And as I told you in the previous video, we need to know phi c equals to 0.65. Those are not given, but we need to know that. And phi s steel river 0.85, and es equals to 200,000 MPa. And as I calculated in the other slide, so epsilon y equals to fy by es, which is 400 divided by 200,000. So it's 0.002. And also epsilon c, which is epsilon c max, is 0.0035. We need to know all of these things. They are not given. You need to know those things. So these are given. Anything here is given, and this is, you need to know these things. You need to know all these things. Now, what is the problem statement? There are three or four components in this problem. Number one, what is the balanced? As you remember, balanced means steel and concrete will fail at the same time, which is never desired, but for the mathematics, for solving a problem. So for the balanced axial load capacity, what is the balanced axial load capacity of this column PRB? And what is also other question is, what is the balanced moment resistance capacity? Moment resistance MRB. And total four components in this problem. It also asks for uh, neutral axis depth, neutral axis depth, and this one is also called CB, I think, CB, and also balanced eccentricity. What is the balanced eccentricity of this column? Eccentricity EB of this column. As I said, what is E or EB? EB for balance, but what is the eccentricity? So once again, similar to the previous problem. So this is the column, and steel river, and imagine there is a cantilever. This is the force P, so the eccentricity is E, and since it is balanced, so that's why it's EP. So we need to find out four problems. What is the axial capacity? What is the moment capacity? What is the neutral axis depth? And what is the balanced eccentricity? Now we can start solving the problem. So before anything else, we need to draw diagram again. So we can draw on this side. So this is the cross section once again. This is the column. Okay. And now what is D1? D1 is from center of this river to the end. This is D1. And what is D2? D2 is from the beam column end to the center of this other column, other river. So this is D2. And if you also draw the strain diagram, so there will be a neutral axis in somewhere in the middle, and remember this is at the steel river, not at the end of the column. This is the end of the column, this is the steel river center. So there will be like this, and this is E epsilon s equals to epsilon y, and this one is epsilon e c max, which is, this value is 0.002 as we calculated in the previous slide, and this one is 0.0035. And remember the other one, the force P location. So we also need to know the EB. So EB is from this neutral axis to this force location. Force location, this is EB. From the neutral axis location to the axial force location is EB. Okay, so now we need to calculate what? We can write once again. We need to write, we can need to calculate PR in balanced, B for balanced, and MR and B for balanced. And we also need to calculate two other things. What is CB and what is EB? So you understood what is EB? From force to the center of gravity is centered. And what is CB? CB is the neutral axis depth. Neutral axis depth from one end to the neutral axis depth. Just check verifying. Yeah, so CB is from this point to this point. This is CB. So we need to calculate EB and CB both. Okay, so first neutral axis depth, neutral axis depth. That is the first step, which is CB. For this, there is an equation CB equals to epsilon C max epsilon y plus epsilon C max multiply D2. And if we now calculate 0.0035, 0.002 plus 0.0035, and what is D2? D2 is from end of the column to the other center of the other river, which is we calculated. We didn't actually calculate yet, so need to find out D2. So we'll come back there. So I can calculate D1 and D2 first. D1 equals to cover, which is 40 millimeter, I think, given. This is the cover. So D1 is equals to cover plus diameter of tie plus diameter of longitudinal bar divided by 2. So you get D1 equals to 60 millimeter. And D2, so D2 is this one from here to the other end, and D1 is from end to the center of the river. So this is H. H is the total depth. This is H. So H minus, I think, minus cover minus D tie minus D diameter of bar divided by 2, and we get its D2 is 240 millimeters. So now we know D1 60 and 240. Now we can calculate CB. We can just multiply by 240, and then we get CB equals to 153 millimeters. So then we get one answer. CB equals to 153 millimeters. One of the part of the problem is done. Now if we approach the second part, for second part we need to calculate the concrete. Maybe we can go to the next page. For second part we need to calculate the total balanced axial capacity, which is PR. PR equals to CR concrete and FR S1 steel 1 and steel 2. So we need to draw one more thing in this diagram. So see in this line, which is like this along this river, if we just put dotted, This is FRS2, and along this length there will be a compression zone. So that this force, this is the compression zone, and in the compression zone the resultant force is FR. Resultant force is FRS1. So this is FRS2, and somewhere here this is FRS1 in opposite direction. FRS1 is going up, FRS2 going down. So this is the summary concrete and one set of steel and another set of steel. For that, first you need to calculate FRCR. CR, that is the zero one, alpha 1, beta 1, C, pi C, F prime C, C and B. So in all these values, 0.8, beta 1 is 0.9, as I showed in the first previous video, 0.8, 0.9, phi C 0.65, this is given 25, and CB we just calculated 153, we just calculated, and this is the dimension of the column, which is 300 millimeter given. So we get CR equals to 537 kilonewton. Now FRS1 equals to phi S FS1 AS1 equals to 0.85 multiply 400. Remember, one is going up, one is going down, one is compression, one is tension. So we're assuming that it's plus 400. And steel diameter, because there are two steel rebar in one side and another two is the other side. So that's a 2 multiply 300. This is the area of the steel, area of river. And since there are two river in one side, so it's 2. So then we get 204 kilonewton. Similarly, FRS2. So it's pretty much same thing, just only one small difference. So it's 0.85 multiply minus 400 multiply 2 into 300. So the only difference is top one is plus and this one is minus. So you get minus 204 kilonewton. Now we get this original equation. PR equals to CR plus FRS1 plus FRS2. So then this and this get crossed out with each other. 537 plus 204 minus 204. So these two cross out each other. So PR is 537 kilonewton. So one thing in this FRS1 and FRS2. So FS1 equals to Fy in compression, and Fs2 equals to also Fy but minus is for tension, and those two things are applied there. So this is the result, PR 537. So you got two component, two more to go. So the third component is moment resistance, that is the easiest one. So as you know, this is the column, river, and this is the P force, and this is the eccentricity, and you already calculate eccentricity. Did we? We calculated CB, we didn't calculate E eccentricity yet. So the moment is P multiply eccentricity. Do you know eccentricity yet? I don't think we know. We need to calculate that. So we know PRB, which is 537 kilonewton, but we still need to know E balanced. So since we don't know E, so we need to wait for the calculation of E. So problem question as E question not balanced, not necessarily balanced, but multiply by E. But in this problem, I need to calculate balanced EB. Okay. So now, so once again, so if we draw the diagram, this is the end of the column and this is the end of the concrete. So this is like that, and this one is epsilon s, and this is epsilon c max. And in this point along this line, this is FRS2, FRS2, and here it acts like a compression zone. So then the resultant is FRS1, FRS2 going down, FRS1 going up. So if we do a, and then this little thing is similar to beam, A equals to beta 1 multiply C, same as beam. So now if we do a moment equilibrium, moment equilibrium, so then if we write the moment equilibrium equation, then we get PR into EB equals to CR multiply H by 2 minus beta 1 C by 2 plus FRS1 H by 2 minus D1 plus FRS2 multiply H by 2 minus D2. So now if we put all these values, 537 10 to the power 3 multiply EB, and then here CR we already calculated, 537 10 to the power 3 Yeah, I just a little bit confused for a second. So 537 multiply, this is CR multiply, not plus. This is the plus. This is the plus, and this is the plus. So this part is one component, and this part is second component bracket, and this part is the third component. So if you put all these values, so you know the depth 300 millimeter by 2 minus beta 1 is 0.9, and you know CBA already calculated 153 millimeter divided by 2. Now the second part, 204 multiplied 10 to the power 3 multiply 300 by 2 minus D1, we calculated D1 already, and then the last part, 204 10 to the power 3 multiply 300 by 2 minus 240. So then if we do this calculation, so we get EB equals to 150 millimeters. And last part, so now we need to still calculate, moment resistance balanced. So moment resistance is PRB multiply EB. So we know we just calculated what is the value, 537 multiply 150. So this is 537 kilonewton, and this is 150 millimeter. So then we can get the value, which is 80.6 kilonewton meters. So those are the answers, and this is the momentary resistance value. So, and this is the other problem. Save. So I will post these videos, but you should you need to follow the video in order to understand it properly. Okay, thanks a lot.